out and then share what this thing. Okay, and participants, we have how many? Oh, I got a bunch of people that I have to admit. And then I'm gonna do it in this order. Come on. Christina, Scott, Alisa, Blake, Ahmad Faiz. We have 7 people. I suppose. And we maybe ready to get started. So I'm gonna minimize this here. Let's see, let's go to the chat and see if people can hear us. So. One, two, three, four, five.
Yes, we can hear you. Can you hear us?
Yeah, this is Christina.
Yep.
Okay. So I can hear you and you say you can hear me, so I guess we are fine. I'm gonna close my chat. I'm gonna write down the attendance a little bit later. So we have 2 days left, today and tomorrow. And I thought that today maybe it would be a good idea for us to start sharing whatever we've been thinking of during the class or or based on what we see in the class. So ideally, which is not gonna happen, but ideally, everybody would have had a project or could come now in principle, right? And say, from this class, this is the thing that I believe I can take, adapt, and use in my classroom. So if you are a high school teacher, then of course you have a classroom. If you don't, if you are just a regular, say, graduate student, then you have probably somebody you can teach. If you're an undergraduate, say, if I were to be a TA for a class like this is the topic that I would go to if people would ask me, how is it like? What is it like? But I'm not entirely sure that everybody's ready for that. And so I only talked to 2 people for today. And if anybody else wants to say or show or demonstrate something, I can just, go ahead and proceed at some point. The 2 people that I spoke with today are Christina, who has, I am aware of 2 things that she could share, and she may share more or less. And the other one is Elmar, who's not here yet, but he showed me during office hour yesterday something. So if it is possible, I guess I would let Christina take over for, I don't know, as long as she wants, 5 minutes, 10 minutes, 15 more, whatever. And then we can just listen to her. Elmar is also connecting just now, which means that he's going to go from his lab upstairs probably, or home, and he's gonna share the screen. So Christina, are you okay starting?
Yeah, I can start.
Good, then I'm gonna stop sharing. And I'm gonna let you share and just tell us what you found interesting or what you're working on and so on.
Yeah, so here, let me share my screen. So this is so this is Quantum Flytrap. This is a resource that Maria posted for us to play around with. And it's a pretty interesting tool. One downside that I have found with this tool is it's sometimes a little bit slow to respond, particularly when you're trying to fiddle with all of these different experimental setups. So I'm not going to click on any of these because it might glitch. But what's cool is you can run simulations. Sorry, this is a little fast. But oh no, I do want 10, but why is it going so fast? Anyways, so you can see here, this is the quantum bomb tester that Maria was talking to us about. And what's cool about this is like all of these are drag and droppable. You can click on them to change the orientation. If you want to get rid of something, you just drag it over to the trash. And so anyways, that's not what I want. I want one of these guys. So this is pretty neat. These little guys are your measurement tools, and you can attach, I don't know what these are called, but like little percentages so you can see like how often those things are getting addressed. So yeah, so this is Quantum Flytrap. I feel like high school kids would get a kick out of this. There's a lot of like, this is like kind of like the low-key many worlds tree. So yeah, so this is Quantum Flytrap. I think it's a pretty neat tool. Yeah, so I really like Quantum Flytrap. They have all these different things. There are only a couple quantum gates, but they do have quantum gates. I haven't actually played around with these, but anyways, yeah, any questions here before I don't really have any other I mean, we could click. I don't know if this will work. Yeah, see, sometimes it gives me this error a lot. So I don't know who runs this. But it's not always the most responsive.
Yeah, so I think this is a simulation, but our Qiskit circuit is a simulation, so that's very meaningful.
Mhm.
You go to, they call it quantum education days or something, but they used to be Schrödinger class at University of Waterloo. I brought this here today. I'm not sure if I can share it with you, but when you go there for the first time, they give you a bag with a lot of props in it. One of which I think is the most effective, is the filters, where you demonstrate that if you have two filters and you put them at 90 degrees, then light doesn't go through anymore. But if you put another one in between, actually light starts going through. That's the most effective. And for the experiment that you are showing us, they give people a set of little pieces of transparencies, and you are supposed to recreate the circuit the way it should happen. So that's still good because you actively have to come up with what's happening there. But this is in between an actual experiment with a Mach Zehnder interferometer and nothing, just the thought experiment. So I think this is a good simulation for people to say, if everything works well, then it's almost like I have a Mach Zehnder interferometer, so to speak.
Yeah, yeah. So yeah, I was the three polarizer paradox you can do in here because they have like polarization. This is also all photon based, right? So they have different ways that you can emit photons. I haven't played around with these too much, but yeah. So I feel like this is a pretty neat tool. I think I could probably spend some more time with it and learn what all of these little doohickeys are. So you can right click on things. So this is an optical circulator, whatever that means. So yeah, quantum flytrap, pretty cool. So the other thing I was gonna show you guys is this Sudoku solver I've been working on. Let me compile this. So easy 318 solved, file name 5. Okay. So this is Sudoku. I'm assuming we're all familiar with Sudoku, but it's a 9x9 with little 3x3s. You need the numbers 1 through 9 in every row, column, and box. And I've been working for the last few months to tackle this to make a solver using some quantum principles. So I started out in Java doing this kind of object oriented. And the first thing I wanted to look at was basically loading this with the initial state of the board. And then I started out with just some really basic Sudoku principles. So like we know this is an 8 because it can't be a 1, 2, 3, 4, 5, 6, 7, or 9. So basically we ruled out everything else. And so it can only be an 8. And so that one step solves easy puzzles pretty easily. We can bump this up a little bit in difficulty. Oh gosh. Sorry, I'm on a new computer and I haven't updated Java, so I have to compile every time. Okay, so the blue squares are doing a little bit more advanced calculations. So like we know that this is a 6 because it can't be anything else because of this is the only place it can be in the column. So anyways, all of that is just like basic Sudoku stuff. What I was really excited about was, if it will get there. Okay, this. So what I was noticing when I was solving Sudoku puzzles is there are many times when in a row, column, or box, you can only have two things. So looking at this up here, we have this 3 and 9 pair. those two squares can only be 3s or they can only be 9s. So it basically rules out everything else. And I call these, I mean, essentially they're entangled pairs, because if it's not a 3, it's a 9. And if it's not a 9, it's a 3. And these two guys, because they're at the same, they're overlapped with each other, they can only be there. And so what we notice down here with this 1, 7, and 6 is if these guys can only be 1s and 7s, well, then we know this is a 6 because it effectively blocks out that tangle, which blocks out this tangle, which blocks out this tangle. And so I can solve 3 squares. So I'll solve, sorry, let me annotate here. I can solve these 3 squares in one step because of this entanglement property. And so we'll see those 3 got solved all at once. And so I'm trying this, and it works sometimes. It doesn't always work. But we're able to solve, I'm able to solve medium puzzles. How do I clear these annotations? And then what I've been working on now is when that's not enough. Okay, so here in a second, so now these dashed lines, I'm looking at entangled triples. So in this line right here, for example, I know there are 3 7s in that row. Here, I know there are 3 5s, but because there's this entangled overlap with the 3s and 4s, I know that this green one is a 5. Because if this is a triple and there are these guys that are overlapped anyways. So this is, I've been doing this in Java or object oriented, but I'm getting to the point with some of these that I get stuck. And so now what I want to do is I'm working in Python. And I want to build state vectors for each of these. So this is a little bit harder to see because it's so small, but I've now changed each Sudoku box into effectively a state vector. So for every square, I have this state. Hang on, can I change my color? I have this state S that is equal to some coefficient. Let's call this coefficient 1 times if the, so the coefficient is the probability of it being a 1, or the squared, plus C3 for 3, plus C8 for 8, plus C9 for 9. And so what we can do now that we have this state vector is when you have that initial population, if I know something is a 1, for example, if I know something is a 1, the coefficient for that 1 would be a 1. And that would mean that all of the other coefficients immediately collapse to 0, because I know that this guy is a 1. And so if I have state vectors for every place, where did my Python go? Now I can start to make decisions based on those probabilities. What's interesting here is 1 over the square root of 2 is 0.71. And this would mean that I have a 1/2 probability. And that's when I'm getting into those entangled pairs, where if there are 2 numbers that each have a 50-50 probability, their coefficient would be 0.71. And so in my Python excursion, I'm looking at now entangled pairs here. And what I'm trying to do, and this is where I'm a little bit stuck, is, let me switch back to Java for just a second. When I have overlapping entangled pairs, so like this 6 and 9, so this 6 and 9, this 9, and this 6, and trying to kind of combine those state vectors into something that's meaningful, that's where I'm a little bit stuck. But this is the project I've been working on, and I'm not necessarily coding it with quantum hardware, but I'm using kind of the logic from these quantum algorithms and applying it to a Sudoku solver. So anyways, this has just been like a side project of mine that I've I just kind of code this for fun every once in a while. And I've solved a whole bunch. So this is my solved list. And then as I add things, this guy was solved at one point and is now broken. So I don't know what to do about that. But anyways, that's what I'm working on. If anybody has questions or anything, I'm happy to talk about it. But those are my projects.
Maybe just a quick comment. It's very, very cool, very impressive, I have to say.
Well, thanks.
Do you use a fixed length vector here for each of the Sudoku box?
Say that one more time.
I was asking, do you use a fixed length vector to represent each of the Sudoku box? Yeah.
Yeah, so the length of the vector is the size of the puzzle. So I didn't show you guys in Python, I can make it 4x4, 9x9, or 16, or it's variable, right? So the length of the vector is the size of the puzzle.
Oh, okay. And when you have when you mentioned about the case of 1/2, uh, do we have does the puzzle break in that case, or can we solve?
So these guys that are in red here, these would effectively be 1/2.
Yeah.
Right? So in Java, I'm doing it more object oriented with like hash maps and hash sets, and I have all these crazy like linked list, nested linked lists of entangled pairs. Like it's ridiculous what I did object oriented to try and do the logic. So now I'm trying to do it in Python, and I'm trying to have I'm still doing it a little bit object oriented, but I've created states. And so now these states have a size and all of the coefficients and all of that. So
okay. So but it is not like it is still solvable if the coefficients are same for two.
yeah, well, the idea here is that like if the coefficients are both essentially 0.5 or 1/√2, and they're in the same box, then I can start to make decisions, like how I knew this one was a 5. I mean, I'm not there yet in Python because I haven't gotten to triples yet, but this is still a work in progress. But like, because in the circle here, I know is a 5 because the 1, 8, 3, and 4 are all trapped in entangled pairs. So that's what I'm trying to code mathematically and not object-orientedly in Python.
Yeah, I understand. Like I was asking because I was wondering if we can maybe use some bitwise operators for like resolving those entangled states, since we're using vectors anyway.
Huh.
But
yeah,
yeah,
well,
like
so
I think that would require like more thought. Just a passing thought that probably we can use some bitwise operations.
Bitwise operations. I should think about that. Yeah, that's a good point.
Okay. Thank
Thank you. Yeah. All right, Professor, what are we learning today?
Hang on.
Or is Elmar presenting too?
Just a second. Okay, so I have the audio on. So this was very good, and I'll take the screen away from you. Thank you so much. And then with the screen back to me here, let's see where I was. I want to just make some comments. First of all, I think that the main point, it's difficult. So back in 2020, we had a workshop that I showed you at CXC. And one of the people that presented was Maria Mihailova. And if you click on her part, there's a description as to why she was there, what she was going to do, what couldn't be done at that time, and so on. And she was working with still working with Christas Vor, who was top in Microsoft Quantum. And she's been very active since. Okay, for example, the book that you're looking over here, Programming Quantum Computers, comes from a group of 3 people. Nick Harrigan and Mercedes are both top-notch physicists, and Eric Johnson is a person who works in a lot of fields, but his main, I guess, expertise is in programming and computer science. So he finished at Berkeley, And then he started working, he went to Bristol in England, and then I guess you can click here to see what he did. But in the end, all three of them are at PsiQuantum, which is the company that Terry Rudolph, among others, has established. The connection with, I mean, James Weaver is doing IBM, and Will Oliver is MIT, and the connection with Maria Mikhailova is that this book, Quantum Computers, is a own type of programming in JavaScript based on Eric Johnson's models. But the good approach that they have taken is that for every exercise in any chapter, they offer solutions in 4 or 5 languages. And Maria solved the Q# solutions. And then I don't know who did the Qiskit. And then, of course, they have a bunch of other languages. Now, these languages are somewhat obsolete, some of them, just because IBM, whatever is based on IBM has been upgraded, and now there are some glitches. So her main focus at the time was, I'm not sure if I wrote it over here, creating quantum katas, which are small individual components focused on one concept, such that you would be able to implement them with Q#. This is Manning Publishers, and there's lots of books over here. She started writing a book recently. Actually, it was September last year that she told me she has a book in the works. But at the time, it wouldn't be available because it was just 2 chapters. So she wrote the 3rd chapter, and June 27 is when this book was made available in the Manning Early Access Program. Now, if you look into our website, where it is somewhere in here, I said that this week I'm going to post this, whatever I have, 3 chapters. And I haven't yet, but I will. And if you click, the last time, I guess I did something on what's new was maybe whatever I did on Monday. I said these 2 books will appear on your list of resources in Canvas, and I will post them tonight. So this is her book. As I said, she presented over there. If you go onto the dashboard, there's more stuff by her than just that book. And so you have a list of 5 projects. They are notebooks. You purchase them, and then you can just click and go through pages of instructions. So what she did was basically BB84 key distribution protocol, teleportation, superdense coding, preparing the quantum state, which is how her this new book starts. Only she does it both in Q# and in Qiskit. And then she has 2 applications of Grover search, one to recover an ISBN, and second to solve a cryptalgorithm. So when you look at what a cryptalgorithm is something that is related to what Christina has been working on. They are puzzles where you're given an expression, and the digits have been replaced by letters, and you are supposed to find out what's behind every letter. So there is some connection. If A is the same digit, then you know that all of them are the same value. If you find it once, then you found it everywhere, but then also you have to find all the other digits. So I think March is when I met Christina at the workshop in CC this year, 2024. And we talked about the number of things, experiences she had with groups of people that promote quantum and so on from the American AAPT, American Association of Physics Teachers. And she said, I'm solving Sudokus, and I want to apply, I'm already doing this, but my goal is to apply quantum principles, which is what she showed us today. And I said, oh, this, for example, this, you should look into this. And then she says, she told me about 2 weeks ago, I looked into it, and it's not what I am doing, but it's related. So how about I show you what I'm doing right now? And that's what I saw. And I thought that would be a good demonstration of what somebody does that could be related with, I mean, a relationship now exists with both what we did in this class, as well as what she could at any moment bring up in her classroom. So what I noticed, for example, if you go back to the main topic, therefore, for me, was there was some entanglement of some sort. If I go on the thing that I showed you earlier, the thing that basically no longer allows us to use this symmetric approach to keep the Misty state formalism free of any coefficients, I think that what she's doing is in some sense, with respect to entanglement related to this circuit over here. Because these produces entangled pairs, but not in the sense three qubits, and there could be like 9 qubits. So these are W entangled states of n qubits. And the example for this class and on this screen is with 3 qubits, but it could be with any number of qubits. The property of, so John Waters also brings them up. I may have a link straight to that place, I think, somewhere on the website 2 or 3 days ago. But what I thought was meaningful is that it wasn't one of the Bell states. It wasn't the GAC state, which says either all 0 or 1, and they have their own benefit. This one says that if one of the values is 1, then the others are 0. So in some sense, if you have a 9 on this row, the only place where you can have it is in this place. If you find it, it's in here, then it's not in all the others. So then kind of selective entanglement in some sense in terms of the values. Like if 1 would be true and 0 would be false. Now, one other thing that, first of all, I very much like her project, and clearly there is some entanglement, but in my mind, there is a distinction to be made, and I may be right, I may be wrong. I'm just telling you what I think right now, like anybody could say anything. So here's my opinion. I think that, I don't know if you guys remember the Monty Hall problem, which basically was saying that it's kind of like the money or tiger, except in that case, you can win a car or nothing. So then there are 3 boxes, and in one of them, there is the information that you have won the car, and in the other 2, nothing. So you pick a box and you don't open it yet, but you pick one at random. You can not do better than random because there are 3 boxes in front of you, so you put your hand on one of them. Now, the person who runs the show opens one of the remaining boxes and shows you that it's empty. Should you switch or should you not switch? That's the question in Monty Hall problem. So if you do not pay attention to the assumptions, then you could get the problem wrong. And a lot of people that are very good in probabilities got the problem wrong because their assumptions were different. So if you assume that the person who has in fact picked, the host has picked the box and then showed you that that box is empty, if the person has done that at random, then there is no reason to switch. But if they done this on purpose, remember that there are 2 boxes which are empty. So if you pick an empty box, there's still an empty box to show you. And if you pick the car, right, there are 2 boxes that are empty to show you. So if they do it on purpose, knowing what's in the boxes, and they always show you an empty box, then you have to switch. There's a bigger probability of winning if you switch, because they took away a bad choice from you, so to speak. So this was something that was very confusing, and it was in the newspapers back in the 80s, and people would argue forever. And this is because of the assumptions. They wouldn't state their assumptions explicitly, and half of the people would work in the assumption that the guy did it randomly, and the other half that he did it on purpose. He will always show you an empty box. So the power of assumptions. We have a problem in the little Qubitzer, not the Qubitzer, the Cubism book, which is exactly the same way. And I told you, if you want to go and look into that book, if you guys don't have it, or if I didn't post it, or if it's not accessible, I have to consider that too, and post it, because if you know how the cubes are generated, then you can find the answer. And there are 3 different ways of producing those cubes. But if you don't know how they are built, then you have no idea what the chance of getting a cube with a side of 0.5 or less. You know, the cubes are uniformly distributed between 0 and 1, the side. So you can't answer the question unless you know exactly how they are built. And this is a very well-known cube paradox. Maybe I guess the name of the guy is Frossen and cube paradox. And if you look it up online, you will find it. Say the significance of the cube factory paradox, and accept all cookies. And this is the thing. And now, if you were to go to, let me see. Let me just go. I want to find Frossen. I got Frossen right though. I want to find it here. So the power of assumptions. I'm going to say something. Where is Wikipedia? There's a page for that. Cube factory paradox. So there's also an assumption here that I'm typing, but then nothing is coming up. So cube, come on. No. Okay, I have to click here to get point clear and yeah, let's do it on Wikipedia. Okay, so what is the assumption? Cube escape, is that it? I have no idea. Where is that one? So is it possible that this is considered to be also related to where is the cube factory? So this is the paradox, okay? And described over here, and in the book, if you say, where is the book? I'm going to say just to show it to you in case we look at the recording again, then I get reminded that I'm going to go to Psalm 22, and then when I come here, the resources are still with password, and as I said, not everybody has access to this, and therefore, because I can't, because some of you don't have a user ID, you just have a guest account that I can use, and I can't type it anyway again. To get into Canvas, but that's all. So if you scroll down and where's qubits at? I'm sorry, where is the cubism thing? Now I can't find it here. Come on, cubism, where are you? Oh, I understand. Now that I'm authenticated, here's what I'm gonna do. The highlight quiz. Can I get to it? No. Just a second, I'll show it to you in a second. So this semester, and then I'm gonna go what's new, and I'm gonna say the highlights quiz. So the question was also, what are we learning about today? But I think Elmar wants to demonstrate something, and then if there's nobody, we can talk about some stuff. But please remember the following: that we have emphasized a particular way of calculating, which is in the book that represents our textbook, combined with something I wrote for you that you can read to see how that could be used in various places. But our goal remains the ability to understand regular books, such as Tommy Wong's book or the introduction to regular mathematical tools. Even though that's written for young students, it doesn't matter. It's the right thing that he's presenting. So what would you still have to do? You know, if you had the time, if we could provide the help, if we be able to meet and discuss and so on, you would have to finish the complex numbers over here. You know, like you did in the very beginning with the probabilities, you'd have to go through these and understand all the properties of matrices. And I posted, I think, 14 out of 18. And then the last part is these 10 exercises, which is all of them from the guide that I'm talking to you about. And so if we wanted to talk about something this week, this would be the topic. We would have to go into the highlight quiz, the Martin Laforêt, and then look at section 4. And I still am planning on doing some of that tomorrow with application to the GAC game. I also have to show you at least where you can read about some more advanced topics that would not admit a simple approach of the kind we were able to take in these 6 introduction to quantum advantage. So we used space kickback, we did Misty States, we did Bernstein-Vazirani, we did Deutsch-Joja, we did Grover, we did superdense coding, we did teleportation, and then we do GAZ. I just mentioned 7 topics, one of which space kickback is not a quantum advantage situation, but it's a really meaningful tool that shows up in other places. So 6 cases of quantum advantage, which can be done with the Misty State formalism or with the extended Misty State formalism. But the point remains, as they were telling us when they reviewed our paper, how exactly is the Misty State formalism relating to the standard conventional mechanism of quantum mechanics? I think Christina at some point said, when you're talking about the break-even point, something at that point in the chapter resembles or reminds me, she said, of some example that you gave casually in the very beginning, and I have to agree with her. I have to choose that example in the beginning a little bit more careful. I really think so. And I thank her for bringing this up. And whether I can do this by the end of the week or next week, I don't know. That's one aspect. This is very important, and therefore, looking into the last chapter of this quiz, this one here, and saying, do I understand what these guys are asking? Because if I don't, all you have to do is to look them up into this document and say, this is really my target. This is where I want to go, arrive and function in basically at the end. So I think that from the very beginning, Terry designed this Misty State not to replace, so Christian is drawing something in yellow. That's good. What exactly would that be, Christian? I'm going to say that I got this from Christian, thank you, and then this is also from Christian, isn't it? We don't know. Maybe that's just random. Question mark. But what I'm saying now is this.
Sorry.
That's all right. So I'm gonna erase them. Is that okay?
Absolutely.
All right. So boom, 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 boom. But I mean, this is very good because this is how we can all write on the screen, basically to communicate our thoughts. All right, so here's the entire thing. There is a goal, there is a target, we are heading that way. And I truly benefited from you allowing me to share with you what I wrote in the Qubits for the sake of supporting Terry's book. Terry's book has 3 parts. The first and the second have been very well addressed. The last one is tricky for me. Without Maria's lecture of yesterday, I wouldn't have been able to tell you that there is in fact that third part. They're called Q computing, Q entanglement, and the last one is Q reality. And I said, there's absolutely no way I can bring that up in class. And she did with her third lecture, and then she asked for a discussion between herself and Einstein. I guess she didn't, the other person asked. And so I was able yesterday in those 2 moments when she disappeared and came back to bring up the fact that the book that we have, small as it is, actually contains that information. And if you look into Terry's website, he says the reason he got into physics was because he wasn't completely sure that he understood what quantum non-locality means. So Q is for quantum. And I hope that you guys have submitted an evaluation for her. And she has 6 questions. I did the same. What I did in so she has some multiple choice things, and then I posted a slides from yesterday, and you also have them in the videos. And at the end, she says, open-ended, tell me if you have any questions or anything. And I said, I'd like to know what's the cheapest way to demonstrate entanglement to a group of people, such as high school students. And I said, I want to bring QBTech to the professional development week next year for whatever that is, maybe in Bloomington, maybe not. But I'd like to know if there is a high school in the UK that has a quantum lab that isn't prohibitively expensive, so that we can establish connections between US high schools in Indiana and UK high schools. One such pair would be enough, and have their teachers come here, have our teachers go there. For the sake of how do you guys do it, I wonder if we can do it too. It's possible that at some point the industry in here in the US might actually suddenly give us an advantage. Right now, I don't think we are at an advantage at all. But we have to find out. So that's what I asked her. So if you're looking at part 3 here, and if you go to page 70, which is 128 in the book, I'm going to go page 70. I'm not sure if I can go like this. I got a 70. That's page 80. Let me go up. And I think he wasn't able to identify the specific pages. I just went for a 70 in the text. And here's the discussion. This is unimaginable conversation between Pooh Bear and Einstein. And you go through this, and it's basically the kind of stuff that she was talking about yesterday. Remember, it's all starting with the EPR paradox. So they wrote a paper, thought experiment, they worked out everything, and then they said, don't you guys see it's absurd? It's nonsense. And they worked out the answer, right? And then they rejected. And she was saying on Tuesday, the moderator was saying, I wonder if Einstein at this stage would be any happier understanding or accepting quantum mechanics, given that back in 1935 he wasn't. So what I want to clarify is that Maria has this unique aspect that she is taking well-established thought, she's taking well-established thought experiments in physics, and she makes them concrete by implementing them in Qiskit. Well, Terry does the same thing here. This is just a draft. So the books that you have that I gave you don't have this thing, and they are finished and they are in one piece rather than 3 pieces. But it was nice of him to make them available for free. Owl puts together a circuit to demonstrate that one of them is wrong. And that's exactly the approach that Maria took. I'm going to come back, close this, and I'm going to say that if you read about him, it's a very, very humorous biography here, which is meant just like him, you know, always sticking out his tongue, just to make it, I guess, more relatable. But he clearly says that the reason he just couldn't get out of this field anymore was that somebody at some point presented a proof of quantum non-locality. So if you're looking at his book, even though the biggest impact seems to be this rewriting system, the last chapter is the one chapter that he can't live without. And with the help of the lectures that she was so kind to give, I was able to tell you that the book that you have, the smallest of all, is in fact the most complete of all. Now it doesn't cut any corners, and then it also brings up the information that that third part is in fact debatable still by many people. Like she said yesterday, and she presented one approach, and there are other people who have different thoughts, and at this point is not entirely settled. I mean, but all the presentations from any point of view have some sort of merit. And back to the Monty Hall that we discussed, I guess the one thing I'm going to close all the parentheses that I started. If I go back to where I came from, this is a highlight quiz. And as I told you, the assumptions are clearly important. There is a link that I couldn't find, and here I will also have to give you this book. This is the book that was written by Hans von Baer. He did not invent Cubism, but he worked with the guy Fuchs, who invented Cubism. It's not finished, but the main statement in Cubism is quantum Bayesianism, is that if you accept subjective probabilities, then all the weirdness that we keep invoking goes away. That's the point. Because the specific perspective that is reality is now being broken. It's an infinity of perceptions, each one from the point of view of an individual. In the video that we have when he presented 4 or 5 years ago at CC, and that pre-symposium day, so Gerardo was there, I mean, online. And then he kept asking questions until von Baer said, well, I'll tell you what, the book was not written for you. And then he said, but I still enjoyed it anyway, Gerardo said. So if you read this, it's a good introduction. It cannot, and it doesn't aim to settle, and from the point of view of the physicist, all the possible little loose ends. And in that website, if you click on his video, towards the end, there are these questions that come from Gerardo until he says, there is no answer for you in this book because it wasn't written for you. And then Gerardo laughs and says, but I still enjoyed it very much. So when you go in here, where's the cube factory? I don't know. I'm going to go and say, let me look for it like this, cube factory. And this is the example that I showed you once that you can read, that you can then realize has 3 different answers depending on what the assumption is, which brings me back finally to the comment I was going to make about the exercise that Christina's working on. It is my understanding that she is solving a puzzle, an existing puzzle. So in that puzzle, if that's the case, I mean, first of all, it's a very impressive piece of work, unbelievably good looking. I mean, 2 implementations, and she has additional resources that she's looking into that's going to make her solver even more impressive. And the fact that you are looking for fundamental quantum mechanics phenomena in such a puzzle that everybody understands is extraordinary, because then the students will be able to relate to it immediately. And then there's a lot of classical programming that goes in there, and they can learn how to do that programming in Java or in Python. But here's the deal. If there is my personal opinion, if there is a puzzle and you have to solve it, all the numbers are in the right places, you just don't know where they are, which means that you are in the situation of working with entanglement in the classical sense, with the socks, if you remember. That's my perspective. If you solve a puzzle, then you're dealing with classical entanglement. And yet they are entangled, right? You know, I have the right sock and you have the left sock, and that's the way it is. If I look at what sock I took, then you have the other one. If you are trying to generate the puzzle, right? At that point, in my view, it is a different story. You're not solving a puzzle. You are creating one for others to enjoy. Then when you are creating, you're dealing with such a bigger space because you don't know where the numbers are going to end up. However, the constraints will still apply. So when I establish that there is a number here, I don't know what number will be there. There will be a certain amount of randomness that will tell me choose between 1, 2, 3, 4, 5, 6, 7, or 9. And if I'm at the very beginning, the randomness says just choose any one of them. Until, you know, at some point you may get stuck. Or you may say, I could have chosen a different one and create a different puzzle. So when you randomly choose one, then all the other boxes on that row and column being entangled are now acting as if they are quantumly entangled because you still don't know what you're going to get, but you're not going to get none. In other words, the setting originally is random, and then it sets the others to something that at this point, it looks more quantum than before. But it's still not quantum because there's too much randomness left. Although we can define, but it's more quantum than if you're just trying to solve the problem. So if you're solving the problem, you try to uncover some relationships that were there to start with. You're not changing those. You just want to become aware of those. But if you are creating a new puzzle, there's enough randomness and degrees of freedom that the kind of entanglement that absolutely exists between these boxes looks far more quantum than in the first case. That was what I was thinking. And I don't think she's generating puzzles. But just the thought that of how she is approaching, I think, is extremely valuable. And then you also say, if something is entangled, it could be maximally entangled, or it could be entangled to a certain degree. And at this point, we could then introduce more concepts to say, if in the beginning, I don't know anything, and I put a 9 somewhere, the others are entangled, but I don't know for sure what they are. I just have a fewer sets of possibilities that I could use, less degree of freedom than what I had before. And eventually, once you know all of them on the row, except one, that one is going to be determined because there's no other option for it. So then you can use a different definition of entanglement that isn't just a simple one that we have at this stage. So honestly, I'm sorry, I had to give this perspective because I like this project so much. So if there are other questions about Christina's project, I would like to invite people to ask or say things. If not, I'd like Elmar to show us what he was going to show us. So any questions?
Well, thank you guys for letting me share.
Elmar, thank you so much, Christina. Really good stuff.
Yeah. So I will share my screen.
Very good.
Wait, can you see my screen?
I guess we see your screen because
You see yourself, yeah. Just a second. Yeah. So I'm not totally finished. Actually, I already lost actually what I have open. So this was something I mentioned before, that we could make an additional output for Misty states. So, and I implemented this quickly, and it should be easy pip installable. And as I tried this morning to get it to Piper, the problem was that they have changed the access and you need to download the API token, and it was just too much of a hassle, and it's not there, but it should work and it should be this evening installable. So the whole idea that I have is this one. You this is now just a baby example. So you install Qiskit, or you load Qiskit, you load the state vector, and then we have as well the LaTeX output. And we generate here a very simple circle. Oh, sorry. So I have now just some wires and some NOT gates, and we generate the state vector out of this. And the idea is now that you could say here, draw Misty states, and it will give you out Misty state formalism. And of course, at the moment it breaks because I have not loaded miskit, but it would then, I load the miskit formalism, and then I can do that, and I get out here the Misty state formalism, and I can compare this to this vector. So always the black ones that are here white are ones, right? And the 0 are black or white, right? It's reverse, and then the ones. So you see that this vector is exactly the same as this vector. Okay, so maybe one more thing. So because Christina was talking about this as well. So kind of we have 8 qubits, and when you look at the state vector, you get 2 to the power of 8, so 64 possible states that you can occupy, because we have computational base 2 in the Misty state formalism. And because I do here, I just hit enter kind of a number, I have 100% probability of one of the states. So this means one of these states, this one here, is the one that get the 100% probability. Of course, you can as well do something like, sorry. You can as well go to the Bell states, and then you get more than one state that have maybe 50% probability. Let me see. Yeah, this should work. And I really am close to where I tried to be, but I didn't got there. And I'm sorry about that. So this is now the Bell states. So is this working? No, it's of course not. I'm sorry. And then I can do state vector from Bell 1. Bell, yes, I should have it. Bell 1, and then gosh, draw what I get. And this is my state vector. And then I can do the same. My control key is broken. That makes the whole problem. Come on. Okay, I just type it again. Bell 1. And then the Misty state formalism. So, right. So, and here now you have two possible states. They are each one to 50%, as we know. And actually there is as well other output. So I think, yes, and of course I messed it up again, but anyhow, so I want to show this one as well quickly because it might be interesting for Christina if she not already knows. The city output. So this one shows you the different amplitudes. Actually, there are now 4 because when it's 0, 0, there are those 2 amplitudes together and those 2. This is 1, 1, and this is 1, 1. Actually, I'm surprised now. I got it wrong point out why there are 4, but I don't recall it. So yeah. So anyhow, that's all I want to show. I just want to show that there is now a way to get Misty State output, and maybe it's useful and maybe not. It was just something I tried to implement. And one more thing. So there is another paper out from Stephanie Economou and from Barnes, and they use actually for each one of the qubits a different shape. So I generated 8 shapes for one word, and they are now ordered that the most the least significant qubit always is the circle, and then it goes towards more and more triangle. That's how I ordered them. Yeah. Okay, that's it. Thank you.
That's great. Any questions? I'm gonna take the screen and see if anybody has any questions. I'm sharing the screen because you mentioned this book. It's called Hello Quantum World. It's from 2 years ago. If we look at a PDF, the point that Elmar is making is that in this paper, they thought they should actually identify the qubit position if it's but this is a single qubit system. This is a gate, this is a gate. But if you have 2 qubits and you have a superposition of 2 qubits, then the square represents the second qubit. And it could be white or black because it's in a computational basis. So I was going to then stop sharing and then share from here. Let's see where share content. I'm going to share from the iPad now. So how do I, the screen, I'm going to share the screen. And I'm going to say that finally it's coming slowly, I guess. I'm going to go into this place and I don't know what this was, but I'm done with it. I'm going to take the eraser and say object eraser and erase everything. So first of all, if anybody has any questions about the system that Elmar developed, please ask them now. As I erase, please.
Not so much a question, another comment for you, Elmar. That was incredible. Thank you so much. And if you are making that installable for everybody, please let us know. Maybe send it out on the group thread or the emails, because I would love to play around with that.
So it should be accessible this evening or in an hour or so when I get this API key. I want to spell check my stuff. So I think this evening I will, it should be available. So pip install Mist kit will do it. So I will of course say it. Actually, yeah. I forgot to mention that, but maybe quickly how I do that. So this is the Python code, right? So can you see that? Can I quickly share again?
Sure, of course.
Yeah.
Go ahead and share. I'll see if I can unshare. Hopefully I can unshare. Where is it?
Yes, I do quickly the structure, yes, and then the entire screen. Okay. Yes, I plan to tell this quickly. So this is actually the code that and it's not that much. So I use NumPy and Qiskit and all
Elmar, I can't see your screen yet. Did you hit share?
Yes, I do. Interesting. Okay, you can see.
I can see it on iPad, but I cannot see it on the.
Yeah, it's like loading.
On the desktop. So could you unshare and share again?
Yes, I can. Let's try again. This is maybe, I don't know. Can you see this now?
Hang on, it's loading.
They do some repair work over there, so I'm sorry when it's loud.
On the iPad, it says that you have started. And
It doesn't. Yeah.
It doesn't say anything. It says that you started, but I don't know. Hang on, let me do one more thing. So I'm going to say replace current share. I'm going to, and now I'm sharing, right? But now let me stop sharing. Now try again one more time.
Yes, and otherwise we just forget about that.
I think you're good now.
I'm good. Okay, so this I load an KitKit and NumPy. I'm sorry they are fixing here something in, and this one is just used to load because I override the function from KitKit. I override this in the state vector. I override the function and I just load this all that I can do that. So I round my values that I get out just to the decimal number 9 behind the comma, because often in Python, even if it's 0, it gives you a very, very small number out. And then here I defined all the shapes, the 8 shapes that I display with Unicode. And then this function here, state to mist, really transforms the state vector into the misty state. That does all the trick. Then that function is the one that I overwrite from KissKit, so state drawer, and I have just copied out the whole function from the original KissKit source code, and I added here that I can give out the misty state and call in this one the function that I described here above, and I added here as well, of course, I updated the doc string and the error message here. The missed state is now a possibility. And then this is actually, when it loads, it will override the old function. It just takes this function and replaces the original function. And it does this when you load the library. So it loads the library and then it just overrides it. I call this function. And of course, this is a hack. I mean, what I should do is I should ask by KissKit if they would like to be interested to add this to their output. And I mean, they could do it. I don't know if they really want to, or I have not tried to ask them, but this is a way how this can be done kind of easily. So yeah, so that's all I want to say. Yeah. Okay. Thank you.
Any other comments and questions? I took the screen away. If anybody else has any other questions, I'm now sharing Shift H. I'm now sharing the desktop screen, and I wanted to say that what he did was essentially at the level of this person's code that I showed you one day without showing you anything meaningful. I said, let's prove that the code runs, and if we run, we get some output. We didn't know what we did. We just run that code. So now what would be this code by Kurgansky irrelevant, or anything that Elmar did relevant? So as far as I can tell, Elmar, it says, if you would like to see the vector state in the state vector, the wave function in misty states, then my code shows it to you. Okay, then once we accept the idea that we can represent it that way, we have to ask ourselves, is it with coefficients or without coefficients? So I think Elmar has with coefficients. Then it's the extended misty state. Because, for example, you can do teleportation in it, but the book does not allow for complex, for any kind of coefficients in the system. So when you're looking at Ilya Kurgansky's code, he just has W's and B's, white and black, and he doesn't have any graphics. And Elmar has graphics with his Unicode characters. They look good, and they are either white or black. And by position, they are something. So maybe triangle is always second qubit, right? And the square may be always the fifth qubit, stuff like that. So we have a difference between which formalism we are using, and then the question remains for both systems: would you be able to guide the student through the individual stages that that they would go through if they were to calculate something? And so now I'm going to have to stop sharing here. I believe that before I actually disconnect from the desktop, I'm going to go into the syllabus, and I'm going to tell you that if I look into the things that we were working on, I first want to remind you that we did teleportation from Barry Bird's book, and where's the thing with C290? I guess, do I have it now? If you go into class notes, and if you go on the students and you click on GRU, and you go into week 6, this is something that we've done. This Bird has this circuit, and this is an important circuit because for the first time ever this class, we are dealing with an arbitrary qubit over here. You may say, but it doesn't have complex amplitudes. I agree, it has real amplitudes, but that's already an infinity of qubits. And the purpose of this exercise is to say that if you give me any state, and let's just say, I just go with real numbers, no problem, okay? There's no limitation of generality. Then what I would like to get from Qiskit at the end, the fact is that Bob is going to have a state that is exactly what Alice had at the very beginning. We cannot prove, because Qiskit does not allow us to create a function, a wave function, or to see the state vector if classical inputs or outputs are being involved. And as a result, we can't let it calculate. It doesn't want to calculate. So we have this inventive approach over here that says, run this many times and collect the statistics and show that your frequencies as measured actually asymptotically in some sense approach the original calculation. So I was asked if this is a coincidence, and it is. It's supposed to be these two numbers, which by the way also by coincidence are basically close to each other. But as you can tell, these two numbers are in fact different, and these guys are the same but completely coincidental. And if you look into the book, and if you run this several times, you're going to get different numbers, and then the experimental at the bottom will be again close to what you saw originally. So one emphasis that justifies Elmar's choice of square, triangle, whatnot, and then Barnes and Rudolph as well as Economo, is that Alice has a qubit. Alice never loses her qubit. It's just that the state of her qubit is transferred. Bob has a qubit. Bob's qubit will change the state to represent what the state of Alice's qubit was. So we have Alice with a qubit set initially to some unknown state. And then we have a pair of entangled qubits that come from Peter. And one of them goes to Alice, the other one goes to Bob. Bob waits until Alice calls him. And based on these two measurements, he applies or he doesn't apply an X and the same thing about Z. Then when he then he doesn't have to measure. We measure because we don't know how to calculate the state vector in Qiskit otherwise, because it involves classical control. But he basically can be sure at this point that he has, honestly, genuinely, 100%, according to the formalism and the calculation, he now has his qubit, his half of the entangled qubit that he got from Peter, the entangled qubits. A pair of qubits were given to Alice and Bob, and that's how they kind of communicate. But his half of the entangled qubit is now in the state that the qubit from Alice was in the beginning. That's teleportation. It's the teleportation of state, not the teleportation of the qubit itself or the mass or whatever. And so that's the purpose of teleportation. And the fact that we're getting an actual qubit with arbitrary amplitudes, real, I agree, but still an infinity of possibilities, makes this unique experiment, make this experiment unique. So then if you're going back to the little qubits, what we really should focus on, we only have a few minutes left, but I'm saying we didn't do this yet. And if you go into teleportation, I'm going to actually just show you what it is, and I'm going to encourage you to see if you can follow the instructions and accept the calculations, right? So like if you were to say, do one thing, what's your one thing on your mind? I did genuinely at this point, if I had the time, I'd go back and work out a better example in the beginning to match what Christina was pointing out a few days ago. Maybe Friday, I'm not sure when. And I will do that for the sake of actually showing you that the 4 or 5 postulates of quantum mechanics can be easily representable in our formalism, extended or not. But other than having to go back and reformulate that example to make it less ambiguous or whatever, I'm going to say that for the first time ever, because we allow coefficients, we're going to look at a regular qubit. And now you know that this is not the most general way in which you can look at a qubit. This is a simplified way, but for us it's general enough. The best way to represent a qubit would be with a density matrix or a system of qubits. And we have this circuit that I sliced. I sliced this to say Alice has a psi, which is unknown, and you saw it. And then the other two are basically zeros. You put zeros and you have this circuit, and this is Peter entangling them. So now the H and the control knot creates an entangled pair between the second qubit of Alice and the only qubit of Bob. And then we have a control knot and an H, and then she makes the measurements. The moment she receives 0, 0, or 0, 1, or 1, 0, or 1, 1, she cannot do anything else other than these 4 cases. She communicates by phone so that the speed of light is not going to be broken, cannot be broken, not that it isn't. She doesn't carefully protect the speed of light. She says, I have to get this information to Bob, otherwise he can't make sense of this experiment. And the fastest way she can communicate this information is going to be with a speed less than the speed of light. And so she calls him and says, these are my outputs when I measure. And based on those outputs, 0, 0, 0, 1, 1, 0, or 1, 1, one of these 4, the gates that Bob has that contain something going on over there will be applied or not. And what comes out of the second gate, whether it's applied or not, on that line, it will be the side that she had in the very beginning. So we emphasize in this class that if you follow along with a misty state formalism with no coefficients, and then at some point you realize you need coefficients, then you can also make the transition as you relate to Martin Laforet's document, that you could switch the formalism and work with what everybody works. And I am going to show that if you could try to follow these steps, you will see that psi 0 is going to be this formula, because there are there is a let me see, where can I show you this? This is a very simple situation. Psi is going to have this superposition. Okay, I did this yesterday with Elmar, and I need to go into escape, and I'm going to say, suppose that you say, I don't know how this was created at all. And I have this situation over here that says, I'm going to write it down, and then still maintain that you could, in fact, I'm looking to see if anybody else came that I didn't write down, so I had, no, but doesn't matter. So I'm going to click on the annotate, and I'm going to say that this will be a pencil. And we have 2 more minutes. So I'm going to at least establish this. Let me get a black and say that this thing is going to be the first qubit. This is the first qubit. And then the other 2 qubits are going to be white, white. This is a system of 3 qubits that comes in here. We have psi, which represents the state of the qubit that Alice is trying to teleport. And then you have, this is psi right here, which is this guy here. And then you have white, white. So how are you going to calculate this? You're going to say, well, this is a superposition. So you're going to say, I have a superposition of alpha white, that's the first term, followed by white, white, comma, and then I take the second one, because we've done this before numerous times, and then beta black is going to be also be followed by white, white, because that's what we have on the other 2. So this is psi 0. And if you're scrolling down, I can't scroll down because I guess I have to go like this. I'm not sure. So I scroll down and I say, see this thing here now I have to go to the annotator if I want to emphasize by writing. This is equals, I guess, and then that's what you see over here, which matches this thing over here. And now the thing is, how exactly would this look if I were to be applying conventional math? And for every single step that I'm doing here with the Misty state formalism, which has to be extended because I need to use the coefficients, otherwise there's no way you can do it. I'm going to say that this is how it would look if I were to use Dirac notation. And I have the exact same thing, and now you say alpha, and then 0, 0, 0, and then beta 1, 0, 0, and then this is the one-to-one correspondence that I think Elmar is capitalizing on when he's using the transformation from the regular state to a Misty state formalism. So we introduce these things in case you are not sure exactly what they represent, and then I apply, I guess, on the then I say, look, in general, if you had a system alpha 0 plus beta 1 and you apply Hadamard to it, by the way, now you can do those calculations as well. And if you follow along, the alpha and the curly braces go outside and you create those superpositions that you had before and you put them together and now you have coefficients and you have an alpha plus beta white and alpha minus beta black. And you haven't done this before, and the white is 0 and the black is 1, then you say, this is exactly what I would get if I were to multiply the matrix for Hadamard with an alpha beta vector for the alpha 0 beta 1. And therefore, you can just go back to the thing and say, I have psi 0, why don't I calculate psi 1 where h is applied to the middle qubit? And slowly, I calculate psi 1, and then I calculate psi 2, and then I calculate psi 3, and I calculate psi 4, and then the last one that I calculate is psi 4. Right here. Psi 4 says, I don't know what you have, what you are going to see, because you have to make a measurement, but the full-blown expression of that is here, and I showed this to you before. I very carefully pull out the first 2 qubits, which are the ones that Alice is going to measure, and they could be factored out, and I have, this is the expression of what Bob is going to experience. You can do this here, or you can do this here. Doesn't matter. It doesn't make any difference. Depending on her measurements, only one of these 4 lines is going to turn out to be true in reality, in the classical world. And depending on which one we have, let's say this one, for example, I realize that if I get a 1, 0, I know that at that moment, Bob's state is alpha 0 minus beta 1, but I don't need the minus. So I can fix the minus by running the z. So I tell Bob 1, 0, which he takes as 0, 1, and then he activates the z, and that replaces the minus with a plus. And therefore, his qubit is going to be in alpha 0 plus beta 1, which is really what Alice's qubit was in the very beginning. Therefore, teleportation succeeded. So all of the calculations are here. It's the first time that we are applying this. And there's a note at the end indicating the ZX calculus based on Penrose notation. This is an older notation. Basically, had the most significant success with the proof of teleportation because you write a circuit in some notation. This is Penrose notation. This is on Wikipedia. It's not the ZX calculus, but there's a similar one with ZX calculus. And through some calculations, things cancel each other. And then the net result of the quantum circuit is that Alice starts with a qubit, which travels to Bob, end of story. And so there was now this debate, infinite debate between the people who invented teleportation and the ZX calculus. One of them says, if you had used ZX calculus, you would have found it earlier. The others, you invented ZX calculus because we gave you teleportation. And it's not clear exactly where exactly the truth lies. But I think it's in a circular way that both should be commended. I think that's the end of today. I thank you, Christina, and thank you, Elmar, for the presentations. I also want to thank you for listening to all of this. We have one lecture tomorrow. We have to wrap up everything. I could submit the grades today. I have all the information that I need, and I might still do it. If anybody needs anything, please let me know, and we can meet and discuss. So this here, let me explain. What you get here is this is a room, and there was Elmar on it, but now Elmar has stopped his video. So we're done today. Anybody, any questions? I guess not. Thank you so much once again for your patience, and let's stay in touch at least one more day. Let me know if you need anything. I'm going to stop recording and then disconnect. And I hope everybody has a wonderful Thursday.